introduction to Shimura varieties.
Okay, so thanks for the introduction and the invitation. And well, my topic is this one. I try to give an introduction to this thing called Shimura varieties and also their compactifications. In fact, I'm not sure why I agreed to do this because this is such a daunting task to try to do this in 3 hours. So when I try to think about how I learned about this subject, what I found out is that it's not very easy to learn from the abstract definitions and also all these correct things to do. So I probably would not try to do the correct things. So I'm going to annoy some of the older people here. So it's probably not completely right. And also maybe I'm not going to give you the definition of Shimura varieties, at least not today. Yeah, so if you want to just learn about exactly what Shimura varieties are, maybe you're going to be disappointed. But anyway, let me see how far I can get. Okay, so I was hoping that there was some introduction to at least modular curves in the first talk, but I guess I have to also repeat that. Okay, so I'll start with the basics. So this is sort of the proto example of this modular curves, and maybe the question might be why we care about them. So Shimura varieties will be generalizations of modular curves. So you have to first have some feeling what modular curves really are and why we care about them. So I guess there are many ways to define them, but I will start with, first you have this, I will start with H, which is all the complex numbers with imaginary part positive. And we know that there's actually some kind of action of this. Well, I guess at least we have introduced congruent subgroups in the first talk. So if you have gamma lying inside SO2Z, then there's and this is congruence subgroup. For those of you who do not know it, this means that this is defined by condition like, well, like mod n equal to some particular kind of type of matrices. So when we say we have a congruent subgroup, it really means it is defined by some conditions modulo some numbers or integers. And if you have something like gamma equal to A, B, C, D, then you can define the action to be this AZ plus B and CZ plus D. And there's actually a way to have a more systematic way to see why we define the action this way. So one way to see it is that we actually think of this A, B, C, D as acting on some kind of projected coordinates. So we put Z1 like this. This actually means the ratio being Z. And then if you just make the action, it becomes AZ plus B, CZ plus D. And now I try to make this equivalent to something easier again. So it becomes this gamma Z1 up to dividing things by CZ times CZ plus D. So this is actually try to make the action on this projected coordinate. So in some sense, we're trying to embed this into P1C. And then there's a projected action on this P1. So this is how you can think about these things. And the action of this SO2Z, or in fact SO2R, actually preserve this line here. This is why things are fine here. Okay, and once you have something like this, there are many reasons we consider the following quotient. So people consider this left action and take a quotient. And there are many motivations, I guess. So one of the motivations is that people try to use this to study the so-called modular forms, modular functions. Those are the functions on the upper half plane which satisfy some kind of equivariance condition defined by the action of gamma. So it's natural to look at this quotient and try to find out what this quotient is like. And this quotient is actually something which is like a open subset of this a Riemann, so-called Riemann surface, a compact Riemann surface. So in fact, there's a way to compactify this thing. Well, in fact, I'm kind of cheating here because I'm just giving you the set. And without the topology, it's not clear what it means by compactification. But anyway, I'm going to cheat a little bit here by just adjoining this with the P1Q. And this P1Q is actually the same subset you can find here. And I don't think I can really draw P1Q, but all these points and the infinity there. So if you put this together, I think it's, I don't know what is the best way to explain this, but this quotient happens to be a compact Riemann surface. And it's actually known that such a compact Riemann surface is actually a curve, an algebraic curve over the complex numbers. And it's very important that we have an algebraic structure because a priori, the quotient of the upper half plane is just a manifold. If you think about it, this is only a manifold. But once you know this is a curve, you can start to ask more difficult questions. For example, you can ask whether this algebraic curve is not just defined over the complex numbers, but actually defined over, for example, some number field. And that is where the magic really comes in, because once you know it is defined over the number field, you can try to look at the interesting invariant of this variety. It's not just about complex topology or complex singular cohomology. We can actually talk about the so-called, for example, atomic cohomology and other things. And those things will have a lot of symmetry on it. So what I would say is that modular curves are interesting for many reasons. So I will consider the modular curves, but not just a single one, with a varying gamma. If you consider this collection, we have two kinds of symmetries which are important. The first is the Hackett symmetry. Well, I'm going to give you a more systematic explanation of this Hackett symmetry later for a more general class of quotients. But this is something quite rather topological. It doesn't require this to be an algebraic curve. So any kind of quotient like this with a variant gamma has a way to carry some kind of symmetry, purely topological kind of symmetry. But there's another important kind which comes from the thing I just said. So there's also the Galois symmetry. Well, this is not terribly precise at this moment, but the point is that these curves are not just over complex numbers, but they're actually over some number field, which you can actually compute and find out. And this is quite important. And in fact, these two things are the main reasons we care about Shimura varieties. So it's actually possible to cook up a large class of sets or manifolds which carry this Hackett symmetry, but they might not always carry this additional Galois symmetry. And this additional thing, this Galois symmetry, is what makes the Shimura variety special among all the things you can write down as a quotient like that. So more generally, we're going to consider a case where this one is going to be generalized. So you can consider larger groups acting on larger spaces. Those larger spaces and those quotients will naturally have all these Hackett symmetry just for very general reasons, because they're just kind of good quotients. But then this Galois symmetry is where you see the difference, I mean, in the theory of Shimura varieties, because it's not true that you can always have something as nice as that. And we will see for very general reasons why it is not true. For example, we're going to see that for some of the quotients, they are like a real manifolds of all dimensions, and they are not going to be complex varieties at all. There's just no way. Yeah, so there are many reasons that you don't have this, and it's not obviously having this by just looking at the quotients. Okay, so I'm not going to say too much about modular curves. I imagine in the last talk today, more will be said about modular curves. So we keep pushing the responsibility to the later speakers, I guess. All right, so I'm going to now define something more general. So more generally, I'm going to define a large class of kind of quotient spaces which will carry the Hackett symmetry. They might not really carry this Galois symmetry. So this one will come later, but I will now focus on this Hackett symmetry first. So these will be the kind of double coset spaces. And the setup is as follows. The setup is that firstly, we need some group. Well, I'm going to introduce the so-called adelic formulation just because this is more systematic. So I will consider, this is kind of vague. So G is, I'm going to write down the terminology, but I might not define them all. I guess this is the compromise. So this first word, I don't know how fair it is for first-year graduate students. Anyway, we will see lots of examples of these kind of groups. I will not really define it. And one thing I would say is that today I will introduce many terminologies without definitions. If I don't define them, then very likely you can find the definition on Google. So please just do that. There's really no point seeing somebody here explaining those things you can easily find online. So I hope I can focus more on things you cannot really just find on Google. So if you put reductive, I don't know which entry comes out first, but I guess the next term will ping down more, like reductive algebraic group. If you put all these in, I think you won't see very strange entries coming out over Q. But this is not exactly what we want. But anyway, let me just say that such that we can talk about the eidetic points of it, well, should I define ideals? Let me try a little bit. So just to introduce the terminology, I'm going to write A is basically there is an infinite part and also away from infinite part. So this means away from infinity. Well, some people don't like this notation. This one is basically just the real number. So I'm talking about ideals over Q. And this one is basically something which I call the Z hat, tensor up to Q. And this Z hat is a limit over all the quotients of Z. And well, there are several other ways to define this. For example, you can define this as a restricted product of the things like QP and ZP. Anyway, I'm just going to write this for the moment. And whenever you have a reductive algebra over Q, you can make some non-canonical choice of things over integers and make sense of the eidetic points. But for simplicity, I will in the following I will always just choose the Z model for you. Well, I put a quotation mark again, so you probably should Google and find out what this means. And what this means is, well, let me just say in words. So basically, if you have any ring, any commutative ring, you will have a group GR. And if you vary the ring, then there's also a map. So if you have a map, so assign GR to R. Well, these are keywords functorially. So if I have a homomorphism in R, then I should have a corresponding homomorphism in GR, and they're all compatible. And if you have the identity morphism, you expect the identity morphism at the level of GR, and so on. This is just for laziness, so I'm going to make an explicit choice of the integral model of these things, so that it is easier to talk about this object. Oh, should I try this? Okay, thanks. Okay, so now I have this G, and let me give you some example of what kind of G we consider. Okay, I think we just talked about SL2, so we can certainly start with there. But for example, you can consider like a GLN, and this R is just any commutative ring. And these are just the invertible elements of all the endomorphisms of this in the endomorphisms. Well, this is kind of a strange way to just write n by n matrices. So those are the invertible n by n matrices. And you can also consider the subring, sorry, not subring, subgroup of elements of determinant 1. And these are the obvious kind of things you can look at, and the usual SO2 and GO2 are just there. Well, I include these examples because these are the most basic examples of reductive algebraic groups. Of course, I still have not defined what they are, but these are the prototypical examples. There are some more interesting ones. Let me now start with something we call symplectic groups. So let me write, so n is an integer. Well, non-negative integer. As long as you can draw this matrix, I think it's non-negative. So this is a 2n by 2n matrix. And when I write something like this, this means the block form, like n by n blocks each place. And then I consider, okay. Again, for each ring, I'm going to define a group. And this group, well, some people might prefer to write SPn, but anyway, I will write SP2n to indicate the size is 2n by 2n matrices. These are all the elements inside GO2n of R, which preserves the following thing. So let me first write down what it does. So what does this really mean? So this Jn actually defines something which we call alternating pairing. And this actually means, well, the alternating pairing is defined as follows. You can define xy to be like transpose of x times Jn times y. So this actually means that if I make the G act on the left of y, and also make it act on the left of x, which becomes making it act on the right of transpose of x, then this will be preserved because this middle thing is just this one. It's the same as that one. So the pairing defined by Jn is preserved by this kind of group elements. You can actually define this group by modifying this Jn. So if you have other kind of pairing defined by other kind of matrices, you define similarly another kind of symplectic group. And the key point is that we need something which is alternating and have some kind of, the so-called large radical in that case. It's probably not completely obvious, but if you look at real points, for example, the symplectic group is actually a subgroup of the special linear group SL2n over R. But anyway, I'm not going to use that, at least not now. Okay, and then also you can define other things. For example, okay, let me say if you have like PQ and integers, now I define that this I PQ to be just this diagonal matrix with the first P entries being 1, the last Q entries being -1, and put 0 elsewhere. So when I write all these block forms, I'm going to freely use the automatic adjustment of sizes. So you have to just think about this as a P by P block, and these have the corresponding sizes. Then you can define, for example, the orthogonal group. Well, let me first clarify that these are not the only ways of, these are just some ways of defining these things. But anyway, I'm going to abuse the language a little bit and call these just the orthogonal group of signature PQ. These are all the elements inside the GL P plus Q. And you can probably guess what I'm going to write. So again, this is going to preserve the pairing defined by this. In case I'm writing too much in the corner, just let me know, because I know that from the back, sometimes you cannot see everything. All right, and this one also has a very nice subgroup, which is this SOPQ. And when I put S here, this just means the determinant is 1. Okay, so there's also a nice subgroup. This is a special orthogonal group inside. Later, we're actually going to see other forms of these things. So even for the same group, after isomorphism, you might have more than one way to define them. So everything I wrote so far are reductive groups, although I don't know how obvious they are. Okay, so we can have natural generalizations of the modular curve case by having groups like this. And you can consider the z points of this group and consider the similar kind of congruent subgroups, and you can have natural generalizations of gamma we had. Now the interesting question might be what kind of things you can X on. So that is a question. And in fact, I didn't really finish the thing there. I mentioned double coset spaces. So what double coset spaces, right? It's not obvious. So let me start with something very general. So suppose GR X on some D. I'm not even making it clear what D is, just some D. And now we'll consider the following. For each, well, this is, I guess the first time you see this, it's not obvious what it means, but let me first write down what it is before I explain it. So consider for each open compact subgroup, I'm now talking about this finite adelic points. When I put infinity on the top, it means away from infinity, which means the finite part of it. If you have not seen these kind of things before, typically this is like all the z hat points of this G, but they don't have to be. They can be just things which we call like commensurable with that. So if you can find some common finite index subgroup which looks like that, then we can define the following. So quotient from the left by GQ, and we consider this D cross G finite identity points, and then we model U from the right. But somehow I have to explain how the things act. So this thing acts diagonally. So it really acts simultaneously on both vectors. And this is possible because we have a GR action on D. So you can, GR contains GQ, so you can have this. Well, I guess I didn't really make it clear you should contain, but anyway, you have a morphism to there. But in all the things we actually cared, it will be, for this reductive algebraic groups, it will actually be containing GR. This U only acts on this second vector. And also, let me make it clear that the reason I put it on the right is because it's a right action. So I just naturally multiply things on the right. I put it on the left because it's a left action. So this right and left is just some kind of convention, but it's just a helpful thing to make these two things sort of independent from each other. But they're not completely independent of each other. So later we will see that we can actually rewrite this double coset space as something more kind of manageable. But for now, let me explain why this is good. So now we can consider all these with varying U. So this one now is now varying. The conjugation action of the group elements of the finite, the G finite identity points actually permutes all the U we can consider. So if you consider all the U together, then you guys just have some kind of conjugation. So if you have U, you can send it to like G, U G inverse. You can certainly do that. And what does that mean? That means that if I consider any topological invariant, for example, of this collection, so now I have to probably assume that D is something good enough. But let me first write down what I care. So for example, if I consider this inductor limit of all the cohomology of this XU, well, of course, I have to require this D to carry, to imply that this is something you can do with reasonable D. You can talk about this inductor limit. Then this thing has a natural action of GA infinity. And this is actually where we can see the link between this and something we call the Hecke symmetry. And this is actually something very abstract. You can have very general kind of D, and this still makes sense. So this actually is the source of the Hecke symmetry. And in fact, if D is something which we call Riemannian symmetry space attached to GR, then this is actually closely related to the automorphic representations. So if you consider all the, well, not all, but a large class of automorphic representations which contribute to the cohomology of these kind of symmetry spaces or their quotients here, then you can actually see the kind of finite identity part of those automorphic representations. Yeah, so this is the very abstract kind of topological reason why these kind of double coset spaces are nice. They naturally encode lots of symmetry just coming from this quotient. It doesn't even matter what D is. Just anything with a reasonable action of XU can make sense. So D can, for example, be like a symmetry space, as I said. It can actually also be bundles over a symmetry space. Then you naturally have more complicated kind of cohomology, which give you non-trivial coefficient systems and so on. So you can actually play with the D you can put there and have lots of different interesting things there. So I don't know whether it's fair to say so, but Hecke symmetry is a bit cheap. They just come easily. As long as they have a set like that, you have the Hecke symmetry. The more miraculous kind of symmetry is not easy to get. And the first goal will be to at least have something which is algebraic, which is not obvious. So what are the Ds we consider? By the way, I'm not saying that you should only consider those D's where you have algebraic varieties. In fact, I think probably Frank is going to talk about something which is not related to Shimura varieties in a similar context. So let me come back to here. So let me start with the examples. Well, in fact, this might be a non-example. Okay, so let me first write down what it is. So this SLNR actually acts very naturally on a kind of space. N by N real matrices, positive definite, determinant equal to 1. And the action is like if you have any G there, then you send X to just this conjugation like this. So if it's positive definite, then after the conjugation, you still have something positive definite. And determinant is okay because SLN has determinant 1. So it's really an action. But unfortunately, what is the dimension of this one? So if I call this Sn. So firstly, what is this Xn? So you can probably show, well, this action is transitive. Very nice. You actually even have a very special point there. Stabilizer of 1n is actually, well, what is the thing preserving this? This is the orthogonal group I've defined. Well, if I write On without the second entry, I just mean the one with the second entry being 0. So this implies that this space is actually not hard to describe. I can actually just model. I probably need to write SO because it's SL. Okay, it's like this. But this one, if you just look at this space itself, this one actually has, for some odd dimension, when A is equal to 3, for example. So for n equal to 2, we get the familiar thing, which is SL2R, model SO2R. And I would like to check this. This is actually the same upper half plane we had before. So for n equal to 2, you have something familiar. But for general n, might get odd dimensional space over R. And it's not going to be a complex curve or complex variety at all if it's odd dimension. Did I? Oh, I didn't. I write positive definite. I guess it's some people's convention that positive definite always mean symmetric. Yeah. Of course, I don't know how you talk about positive definite without that condition. Anyways, thanks for remarking about that. Yeah. Well, you can easily calculate the dimension because you know the dimension of all the symmetric positive definite matrices. The positive definite condition is only an open condition. So what is important is the symmetry condition. And for n equal to 3, you know the dimension is actually odd. So this is some kind of good space only for n equal to 2, but for higher, it's not really good enough. But this is still a very interesting space by itself. And in fact, when you want to study automotive implementations, this space itself can provide lots of interesting sources of cohomology classes. The only thing is that we don't really have natural Galois symmetry on this, the cohomology of these kind of things. But we are going to have more interesting things. So we will try to, we'll give nice, I'm going to be vague here for now. It's algebraic, and I'm just going to give you examples. I'm probably not going to give you the proof. It's actually not easy to prove anything like this, but I'm going to give you examples where this is true. And also, I have not really made it clear why we have something gamma like there. So let me at least explain why that is the case. So why do we have any gamma in this picture? So I'm going to cite a general fact, which is that if you consider this following set, now I'm only taking the quotient without a d there. This space, well, as a set, the cardinality is finite. Well, I'm not terribly precise at what I mean, but this is what is true. I learned this from a paper by Borel in the 60s. But what it implies is that you can write this xu, which is by definition this quotient like this. And how do you improve this expression? So I can rewrite as follows. I guess I'm cheating a little bit, but let me write this way. I still have d here, but this middle thing, now I have some kind of representatives. They are not canonical, but they can be there. Yeah, I replace this middle set there as a disjoint union of some subsets. And now if you now check what this double coset is, there's a lot of cancellation because on the right, this u action will be absorbed by this this kind of double coset expression. Then the question is about the left-hand side. It's amazing how quickly it becomes this again. So, well, I guess I'm going to skip some details of this exercise. This is actually the quotient like this, where this gamma I is just this GQ intersect GI inverse. Well, I hope I didn't make a sign mistake. In the worst case, you switch the signs. And each of these are something which are like the z hat points of the group. So if you intersect the z hat point with the q point, you get something which is quite similar to gz, but not exactly. This is something close to being gz. So this is something very close to this congruent subgroups we had in the case of upper half plane. And this is something we will basically call arithmetic subgroups. And then you have the quotient like d by this. I'm still not specifying what d is. So I guess the point is that for suitable d, we want this thing to have a nice structure. So for example, later we want this thing to be like quasi-projective variety. I mean, something which naturally might have a definition over a number field or so. So we want and if there are algebraic varieties, there are many natural things we can do. Well, I guess it's not necessarily so, but having an algebraic variety structure allows us to do many interesting things. I have to emphasize that apart from just the Galois symmetry, there are also a lot of other things we care about once you have this algebraic structure. So for example, often we can actually have not just a rational structure over some number field, but in fact the structure over some integer, rings of integers over there. And it makes it possible to talk about congruence in a way which is not obvious. So if you talk about the congruence only using the abstract topological structure, you get some congruence, but that's not the only way you can get it. Because if you have an additional structure from here, if you look at the coherent shift cohomology, for example, you have actually another source of congruence, I think, which is far from obvious. So if you look at the quotient manifolds, you don't really see them. And the reason is that if you think about it, even in the case of upper half plane, having a quotient gives you some coordinates which are like modular functions or modular forms. They're quite transcendental compared with the coordinates of the upper half plane. So we're actually using that kind of transcendental thing to do congruence in some sense. So these are far from obvious. So this also allows not just, like for example, Galois symmetry, and also non-obvious or non-trivial congruences. And in fact, in some cases, we actually use these non-trivial congruences to create Galois symmetry. So there are something which is not very obvious if you just look at the topological structure of all the double coset spaces. So if you come back to here, on this kind of thing, like SL2 action on this kind of symmetric space of all dimension, it's not quite obvious how you can get the second kind of congruence. But if you have something which is really algebraic variety, you have some miraculous kind of other source. Yes. Oh, one more. Okay, thank you. So I'm still not telling you what D I'm going to use. Okay. All right, so I think I should at least talk about one very important D before the day ends today. Well, maybe for me. So I told you to use Google, so I should at least give you some terminologies, right? So we want D to be, well, to be more precise, there are finite unions of the so-called Hermitian symmetry spaces. Well, more precisely, Hermitian symmetry domains. Well, if I start to define all these things, it would take a whole hour away. So I'm sorry, I'm not going to define them. I think even by Googling them, you will see a lot of technical definitions which are not very easy to absorb. Fortunately, there are actually not too many kinds of them. So it's quite likely just in these 3 hours, well, I already lost almost an hour, we can probably list all the important special cases of all the symmetry domains, which are Hermitian. So I don't know whether it's lucky or unlucky. There are just that many kinds of them. Yeah. So I will start with the easiest kind, which is a direct generalization of the upper half plane. So I will start with the first example, which is the so-called Ziegel variety case, where we work with a symplectic group. Well, I already explained that this SLN is not going to work. So you might wonder whether this is the only thing you can act on. Well, the point is that in this case, well, there's a complete classification of all these things. And it's known that for SLN, unless n is 2, you don't have a nice space, which is Hermitian symmetric domain to act on. Yes, unfortunately, SLN doesn't have a nice D to act on. The terminology will be that sometimes you hear people say, well, this group has no Shimura variety. That's what it roughly means. Another thing I want to clarify is that I'm not really talking about Shimura varieties at this level because I'm taking this disjoint union of all these things. There are in some sense only the connected components or some unions of them. They are not exactly the Shimura varieties. And there is some kind of subtlety about the connected components, how many of them you can have. And one way to think about them is as follows. So a priori, you can have many connected components. Each of them is defined over some larger number field. But they are in some sense the Galois orbits of each other. So if you have many of them, if you group them together, they can actually descend down to a smaller ring or smaller field. So in practice, there's another kind of subtlety there, which is something encoded in the so-called Shimura reciprocity law. And I apologize, I'm not going to really explain about that. That is what people actually have to explain when they claim they want to explain about theory of Shimura varieties. So I guess I'm going to be cheated a little bit. I'm not going to tell you that because, well, anyway, I'm going to first tell you what these Ds are. And if we really have time, maybe on Wednesday I can say a little bit about how you work with those subtleties. For now, I'm going to focus first on the connected components and see what kind of things you have. And you might wonder why it is useful to have all these examples. I mean, it's hard to say because in the end, once you feel tired about all these special cases, you want to go back to general theory. And in some sense, you will eventually learn that. But the question is how you get to that stage. It's not always easy. So my job is to make you feel fed up with all these examples, and then you will be so motivated to look at the general definition and understand them. You might hate me, but in the end, you learn the stuff, so I'm happy. Okay. And I included type E in my abstract. I don't know whether I can get there, but I guess when you see E7, you are going to be fed up anyway. So, all right, I don't know whether we have time to do that. Yeah, so I just remarked that we'll focus first on the connected components. So I'm sorry that I'm not going to mention Shimura reciprocity or anything like that until Wednesday, or even not even Wednesday. Yeah. On the other hand, that is a general theory you can probably just learn abstractly. On the other hand, all these examples can be helpful. I think when I started learning all these things, I I was given some kind of task of trying to understand what happened on unitary groups. It was very frustrating in the beginning because there are many ways to write the coordinates. And I didn't know how to do the right choices, and that took me a while to really understand. If you look at the literature, it's all scattered, so it's not very easy to find. So anyway, I'm going to write down some things which are probably out of nowhere, but I hope you will appreciate some of the explicit examples anyway. I think I can still keep this first line, right? Okay. Okay, so as I said, I'm going to start with the so-called Ziegel case. Well, this really doesn't tell you what the group should be, but this is the case when the G, to be more precise, there is a subtlety here, so sometimes people consider the so-called similitude groups. Let me first write down the case, which is easier without this additional structure. Okay, I have this thing, and I now make it act on a space, which I'm going to describe. So I denote it by H sub n. This is the generalization of upper half plane. These are all the, well, what is a good notation? Let me write this way. I write sim sub n c. This just means the n by n symmetric, which satisfy the statement that imaginary part. So if I take the imaginary part of this kind of matrix, it becomes a real symmetric matrix, and I can ask whether it is positive definite. Okay, so this is probably the easy way of describing this so-called Ziegel upper half space. This generalizes the Poincare upper half plane I wrote earlier for SL2R. Of course, just by writing down these things, it's not clear how the things work. So although it's not absolutely necessary, let me write down slightly more information about, and slightly more about these things. So of course, the reason I wrote it down is because there's nature action. So the question might be, how does the, so if I have G lying inside this SP to an R, I want the generalization of the usual Mobius transformation. So if G is, well, now I'm going to write this as a block form, A, B, C, D. Each of the block is n by n. Then I have GZ acting by, well, now be careful because these are matrices. They are not commutative. So, well, I want to imitate what we have done. So I write this way. But I'm going to explain a little bit why this is correct. I write the inverse on the right, but I guess you can design your own choice. So I have to explain why I make this choice. So this is just because, for the same reason, I'm doing a left action for some reason on this space. These are now block matrices. They are all n by n blocks. This is just AZ plus B and CZ plus D. But now I'm going to make a kind of more general kind of projective coordinate. It's not really projective. It's actually some kind of Grassmannian coordinate. So I'm going to divide by CZ plus D on the right. So this is actually the same as this GZ1. Now I'm dividing on the right. And there's some reason for that because I'm acting on the left and I make this choice on the right. So if you don't like this left action, you can just make your own choice, but then you have to write everything your own way. It's just a matter of realizing what you have. But it's probably still not obvious why that thing is preserved. So let me tell you the way I think it is preserved. And this actually generalizes to other kind of so-called classical groups. So once you know how to work with this example, you know many other examples at the same time. So for example, I would like to rewrite this as follows. I write Z as all the matrices n by n, which satisfy something as follows. So this is the Jn I had, if you remember. This is the Jn I have. I will put Z1, transpose Z1 on the left. and I would declare this to be 0, you can check that this condition is equivalent to the condition that you have a symmetric matrix. So this is the condition, you have a symmetric matrix. So this is sort of equation 0. Well, we have well, in fact, this is equality. We also have an inequality. So now I take the transpose, sorry, not transpose, transpose and conjugate, and also have this. I don't remember the sign. Let me hope I have slept enough. Okay, this one is actually equivalent to the condition that the imaginary part is positive definite. Well, if you don't like positive definite, you can change it to negative definite and just change everything. So why is it obvious that Hn has the action of the symplectic group? It's because all these conditions are defined by this Jn. And Jn is preserved by the group G. And G is a real point, so it doesn't matter whether it's a complex coordinate or whether it's conjugation or not. So these two conditions are preserved by the real action of the symplectic group, sp2 and R. Yeah, so this is another way to see why this domain is the correct one. So if by any chance you have to rewrite your domain, you just do the same thing. You just put down your new choice of Jn, then you have all the equations you need, and that will be right. Of course, these are all kind of ad hoc. I have to say that there is actually a beautiful theory behind all these, but I'm not really telling you that. But if you really feel interested, there's actually a way to pursue and understand why these things are true. Anyway, this is sort of the way you can actually see why it works. Okay, so we now do have an action there. Getting almost there. Okay, so this is only an action of this on this Hn. I don't really say anything beyond that, but I can actually say, for example, this action is transitive. So how do I show that? So to show transitivity, you just have to show that you can move all the points to a single special choice of a point. So move every point to I times In. Okay, I claim that I can move all the points to there. So how do I do that? Well, there are obvious elements in the SP. You can check that if you have something like 1 minus x, 0, 1. So let me say if I have z, which is x plus iy. If I make this act on z, then I actually have just shifting by minus x, and I get my iy 1. So I can always make a translation and then move it to a case when you have no real part. That is easy. And there's another choice. For example, if this is actually also an element. Well, this is actually equivalent to having an action of A on the left, transpose action of A on the right. And if you choose the correct A, this becomes, well, just diagonalize. So yeah, so you can actually move all the points to a single one. So this is a transitive action. Well, for those of you who wonder why I do this, just be patient for another 5 minutes. There's a point we try to get to. So now that you know it is transitive action, now the second question might be, what is the stabilizer? The same question we have asked in the previous examples. I'm probably not going to check in detail for you. Stabilizer at this are all the elements of the form inside this sp2n. Well, I'm kind of lazy here. This hides a lot of conditions in the defining equations. But in fact, this is isomorphic to another group I have not yet introduced, which is a unitary group of size n. well, I put it this way, but in fact, this is all the complex matrices which preserve a Hermitian pairing, not, well, this looks redundant, but I'm going to put IN here to emphasize that we're actually preserving something. It preserves the trivial kind of Hermitian pairing defined by IN. And the isomorphism is by, if you have A and B, you just correspond to the A plus IB. You can check that this is isomorphism between the two things. So this actually gives you isomorphism and this is actually an important one because this UN actually happened to be another group which also have an interesting interpretation. So far I'm just working with the domains and just work with this kind of abstract things. But there's another way to view this domain, which is meaningful. And this meaning is actually very important for the applications. Namely, I'm going to relate this thing to some kind of modularized space, so-called modularized space, which are sort of parameter spaces in a rigorous sense of things we call abelian varieties with polarizations. So I have to explain how you get there. So this UN happens to be the following thing. It's actually, well, let me first write down what I have and then explain what the notations are. It's a centralizer of the following map. In fact, let me be careful. This is only U1 here. Well, this G, I didn't write G, sorry. This is SP2 R. How does this work? So this U1 has elements which are of the form like A plus BI. Then I just map it to, I don't remember which sign convention is right, sorry. I will just take one. If it is wrong, just tell me tomorrow. For the centralizer, it doesn't matter which one you take, but for the interpretation, there is some subtlety about the sign convention. Why is this interesting? So why is a centralizer? This means that so basically this is the stabilizer under the conjugation action. Wow, I keep writing G. Sorry. On this H naught. So you can consider all the, you can consider all the possible collections of this H satisfy some conditions. I'm not making clear what those are, but you can make this G act on these kind of things of the conjugation. Then you get all the other kinds of H, which are conjugates of this H naught. Then this actually implies that this Hn is actually isomorphic to GR acting on this H naught. So it's actually an orbit of some kind of nice group homomorphism. And what does this group homomorphism mean? There's actually a meaning of that. So there's a particular element here. If I call this J equal to this. This defines something we call a complex structure. On the 2n dimensional space. And it's not just a complex structure, it's compatible with many other additional things we have on this R2n. So now you should think of this R2n as being like equipped with additional pairing and all the structures there. So what is good? If I consider the following, consider A naught or AH naught being this, let me call this J naught. 2n mod of Z2n. Well, if I have a complex structure there, this becomes a complex vector space. And this is a lattice. And now you can ask what this really is. So a priori, if you have a complex vector space quotient by a lattice, you get a so-called complex torus. But we're not just working on complex torus. We want something more than complex torus. In fact, we want something we call abelian variety with a polarization. So I guess this is far from obvious. this is a big exercise, I guess, is now isomorphic to Cn mod out a lattice. Let me write down the answer. Well, I hope I'm right. If for z equal to this in, and you shouldn't be surprised that if I have other h, if h is like a g times h naught, then I have z. So let me put z naught here. Then this A, which is also the same as this one. Well, this all looks a bit funny, but this one has an action complex structure J equal to HI. This one is now isomorphic to, I guess you can guess the answer. It is the n-dimensional vector space mod out a lattice. This is just the z. Well, I didn't say what z is. I'm going to say it. Then for z equal to g times this in, then you actually have this corresponding complex torus. So this a priori, this space, this zero upper half plane, a priori just looks like it's just like a trick. You write down some space with an action and it works. But in fact, it has a meaning. And I think this meaning is one of the most important miracles in this whole theory of Shimura varieties. In fact, we can talk about all kinds of Shimura varieties, but the most useful ones are, well, the ones we know how to use are all related to this expression. Like, we can relate it to like a family of abelian varieties. And they are not just abelian varieties. This actually comes with a polarization. Well, if you have not learned what these things are, just take it as a keyword. But to have a nice moduli of abelian variety, you need some kind of polarization, and this one comes with a polarization. And this is actually one of the most important things in some sense. So I have 5 minutes. So let me just mention that, well, I said I'm not going to tell you how to do this Shimura reciprocity and so on. But at least I can tell you that for this kind of thing, which are parameter spaces of abelian varieties, there's a totally different way to construct a space which looks similar. Namely, you can try to write down a so-called moduli problem, which are some kind of functors parameterizing all the possible objects, which are like a abelian variety with some polarization, which are similar to this kind of thing. And there are some other things we call level structures, and also some cases endomorphism structures. If you have those things, then you can consider the moduli problem. And then the basic principle in the theory of moduli problem is that if you only need to write out all the conditions over a particular ring, and if you can represent it, then your thing is defined over that small ring. So if you have very few words you need to write down moduli problem, then your moduli problem is going to be defined over a very small ring. And that is usually much smaller than the complex numbers. You can often write down a moduli problem over a small number field, or even the rings of integers of them. Then you have nice models of them. And when you go to the complex point, you recover the original complex points. So this is sort of kind of the first important situation when you actually can write down nice algebraic varieties. Of course, I'm still cheating because I'm still not telling you why they are algebraic varieties. So I guess I have to wait until tomorrow. Tomorrow or maybe Wednesday. But anyway, I will come back to this point and explain to you why these kind of things are related. Another thing I want to say is that I only tell you that for each h you have some kind of abelian variety and polarization. But in fact, you might have redundancy. So this quotient by gamma actually tells you how to deal with that. So I guess it's not completely obvious why this is true, but let me just write down sort of the fact. So this is not completely easy to justify, but anyway, this is an important fact. This AH is actually isomorphic to, well, AH with the polarization is isomorphic to AH prime with the polarization if and only if this H is equal to g h prime. Maybe I put gamma here for some gamma inside this very special thing. And this is unusually simple. I guess in general, if you have other groups, you don't really have such a simple-minded kind of setup. But still, this implies that points of this quotient when gamma is like a sp2z, 2nz, parameterize polarized. In fact, this case is a so-called principal polarization. But this has something to do with the pairing we choose, so I'm not explaining everything here. Principal polarized abelian varieties over C. This is only some kind of so-called coarse moduli. Just like if you take the upper half plane quotient by SL2Z, you don't really get a fine moduli. You have some kind of endomorphism because of this, some kind of torsion in the stabilizer group. Anyway, and what happens if you have other gamma? So if you have a gamma which is defined by some congruence condition, you can actually translate that into some condition on the n torsion points if you are taking condition mod n. So if you have a congruence condition mod n, it's translated into some kind of structure about n torsion points, and that is something we call level structures. So if gamma is a congruence subgroup defined by condition mod n, then you get conditions on n torsion points on the abelian varieties, and those are the so-called level structures. Well, of course, you can complain that not every group gives you gamma which is inside the SL2nz, so sometimes you have to change your choice of coordinates and so on. That corresponds to some kind of isogeny of the abelian varieties. So the correct way to define everything, you might be to use a so-called isogeny category instead of isomorphism category. But to begin with, I think it's usually more helpful to start with isomorphism category, which is less confusing. So I think that's almost everything today. So let me just give you what we might talk about tomorrow. So I guess tomorrow I'm going to give you more examples. So for example, I'm going to tell you what PL type things are. And also, for example, what are the Hush or abelian types? Well, in fact, it depends on whether we have time. We also can talk about exceptional types. Well, not all of them. And if we have time, we can even move on to the next topic, namely what might be. So for example, in the case of modular curve, we have these rational points on the real line and also on the infinity, which is forming these cusps. So I can probably tell you what kind of cusp you should expect in each of the examples. Of course, there's also a subtle issue about topology, but given that I didn't even explain what the topology is in the modular curve case, I'm going to wave my hands. I'm not going to really tell you the topology in general, but there's a terminology for that. So there's something we call Sataka topology. And again, you can Google and try to understand it. Okay, I'm going to stop here today. Thank you.